Should I drop the lights a little bit so we can... I think it's like that we usually have it, isn't it? So for today, we're going to get to know how piloted double non-return valves work. So on Friday we looked at non-return valves, and we also looked at piloted non-return valves. So now we're going to look at double ones. And we're going to become familiar with flow control valves, so basically restricting the flow when needed. And we're going to get to know how throttle and orifice valves work, and become familiar with different types of throttle and orifice valves. We've already looked at some types of throttle valves in subsea technology with regards to the throttle valve on the Christmas tree. And it's much the same principles that are used in hydraulics also. The whole thing with getting fluid from a well is basically hydraulics also. You have fluid under high pressure in the well that's coming up, and you need to control it. So in a way, it's hydraulics. It's just usually when we're talking hydraulics, we implicitly mean with a hydraulic fluid such as oil, hydraulic oil. But hydraulics could be anything as long as it's a fluid that's moving through it. We're going to get to know how one-way flow control valves work, and we're going to know how flow regulating valves work. So we're going to start with the piloted double non-return valve, and it looks like this, where we can get, if we want to, we can have free flow from A1 to A2, because the flow can come up here, and as long as the pressure on the A1 side becomes greater than the pressure on the A2 side, it's going to becomes greater than the pressure on the A2 side and the spring, of course, then it's going to compress the spring and open up so that we get free flow going from A1 to A2. And the same goes for the other side with B1 and B2. We get great enough pressure on the B1 side, and it's just going to open up the valve. And likewise, we have flow from A2 or B2. It's completely blocked, so no matter how much pressure we increase here, we're just going to keep it blocked by increasing the pressure. It's not going to help us one bit. But when we are sending fluid from A1 to A2, we are also creating pressure on this side of the valve, which means that we are sliding it over to the side, and it pushes on the ball element, which opens up the flow from B2 to B1, which is very handy if we have a cylinder, for an example, where we want flow in one side, on one side of the piston, and we want flow out from the other side of the piston. So then we, just by pushing fluid into the piston chamber, we are also opening up flow from the piston rod chamber so that we can get it moving. And the symbol for these is basically placed inside a square, and we have two check valves, but we also have these pilot lines that are showing that if we get high enough pilot pressure from A1, it's going to push the ball valve up so that we open it up on the B2 side. And the same for B1, it's going to open up the A2 side in that case. So that was the last one of the non-return valves. So then we start with chapter 10, which is the flow control valves. And if everything goes well and I'm not too delayed on my different slides now, so then we should be finished with the book parts, so all the curriculum in the book, by next Friday. So that we're going to finish it off then with getting all the way through chapter 12, which is all of the theory that we're going to go through. So for the remaining lectures then, we are going to just be placing up large hydraulic schematics, and we're going to be interpreting the symbols and doing calculations on the different components and stuff like that. So we're going to do a more practical approach to it afterwards. So we're going to get more into that once we're done with all of the theory. But it's very important to... It doesn't really help having a hydraulic schematic up here if we don't know what everything means. So we need to move through the theory first. So for the flow control valves, we want to be able to change the volumetric flow rate, because for cylinders, the speed at which they extend or retract is dependent on the volumetric flow, and it's the same for how fast a hydraulic motor rotates. It's dependent on the volumetric flow rate. So if we are using a constant displacement pump, then we're going to have a constant volumetric flow rate. So if we have a flow rate of 40 liters per minute, and we're using a constant displacement pump, then we're going to have 40 liters per minute. That's going to be the flow rate that we have. We don't have anything else to work with, so we're going to have to use valves to regulate flow rate. If we for some reason we have a motor, and in order to attain the rotational speed that we want there, we only want 20 liters per minute instead, then we're going to have to use a flow control valve to regulate from 40 to 20, so that we get the correct volumetric flow rates into the hydraulic motor. Yeah, so reduce the rate into a specified level. And we have two categories of them. So for flow control valves, we have the ones that are just called control valves, and we have the ones that are called regulating valves. So the control valves are of the throttle type, and the symbol is shown like this, or they are of the orifice type, and then they have a triangular symbol instead of a curve. So that's just the difference of them. So the question is just how does the cross section of these valves look like? We're going to get into that in a bit. For the regulating valves, then we have the ability to regulate how much is going to. So usually, an adjustable regulating valve, it will be a throttle valve where you can adjust it. So you have some sort of knob that you can turn around, or some of them even have solenoid adjustment abilities where you can give electrical current to a certain level and you're going to adjust it. But that's how the symbol is built then, that you have that adjustment arrow going through it to show that it's possible to adjust it. So we're going to see a small clip of flow control valves. I think there was supposed to be sound on this one. This is more of a larger scale where you're actually running a process. So whether it's oil or something else that you're running through here. This sort of shows a bit how the flow acts when you are regulating it with a throttle like this. In a hydraulic system, you will have the same effects happening on the fluid, even though it will be, of course, smaller dimensions than what this is. But it still gets you to show the effect of how the flow reacts. So we're going to be looking at throttle and orifice valves. So if you actually look in your book, it says flow control and orifice valves, but that can't be correct because they are determining them as throttle and orifice valves. Just to mention that, I think I've put in all of the errors that I found, because in these last couple of chapters I've found quite a lot of mistakes in the text. None of them impact how things work or anything like that. There's not any wrong information there, but it's stuff like this where they've put in a flow control is a general one, whereas throttle and orifice is specific. But they managed to put in flow control and orifice instead of throttle and orifice. So it's sort of basically just bad checking and approving of these chapters, I think. Maybe they were close to the deadline or something when they were writing these chapters. So I've tried to put them in with corrections everywhere where I found them. So the flow resistance in a system is dependent on, of course, the cross-sectional size where the flow is passing through. And it's also dependent on the shape of that cross-section. So is it a rectangular cross-section? Is it circular? What's going to be the shape of it? And of course, it is dependent on the viscosity of the fluid that we're sending through it. And we're going to get pressure drops over valves like this because of the viscous friction. And we're going to have an increased flow velocity since we have that pressure drop. It's the Bernoulli principle all over again, with you are creating a smaller space to go through, so you will, in order to maintain pressure and flow rate, you increase velocity, but you do lose some energy due to friction, so that you also lose pressure and volumetric flow rate. Do you have a question? Yeah, you will have erosion of these parts, but usually it's on the scale where if you're running them at their maximum flow rate, for an example, a valve will have, if you are throttling it down from 50 liters per minute to 20 liters per minute or something like that, it will usually have some sort, in the data sheet for the valve itself, it will usually have some sort of information as to how quickly it's going to need servicing and stuff like that. But it's not going to be often, basically. And usually those servicing intervals are given in amount of hours, so that it's amount of hours in use. And in a system, you don't use it constantly, unless it's a manufacturing plant where this valve is in constant operation 24 hours a day, 7 hours, 24 hours a day, 7 days a week, all year round. Then you can just start counting the hours and looking at how many days and years this is going to be, because usually it's going to be years, because it's often in the millions of hours that it's given. But then you have sort of a lifetime for the valve, so that you can put this into your servicing schedules to either, if you have stopped flow in this part of the system for other servicing intervals, then you can open up the valve and just check, does it still look good? Can we continue using it? Or just basically switch it out while you have a stop in your flow in the system. So if you just switch your valve, then you can do servicing on the valve that you just replaced, and see if it needs to either be refurbished or totally replaced. So that's basically how it's done in the larger systems. And the throttle valves, they intentionally create turbulence in order to create more flow resistance. So that the more turbulence they create, the more flow resistance we also get. But of course, if we get to a certain point, we're going to have cavitation, and then we're going to have serious issues with lifetime expectancy. So they are sort of measured to be create as much turbulence as they can within a safe safe range of flow velocity, so that you avoid cavitation. And the resistance of the orifice is a function of how much turbulence it creates, and it is completely independent of the viscosity of the fluid. So that, but that's the resistance of the orifice itself. So the cross-sectional opening. So it's not the opening itself isn't dependent on the viscosity, but of course the total resistance in the system will be dependent on the viscosity of the fluid. And orifice valves are used when we need to be independent of temperature and viscosity, such as in a flow meter, because you might have temperature changes in your hydraulic fluid. And if you remember from the first couple of lectures we had, when temperature changes, your viscosity also changes. So that by using an orifice instead of a regular throttle valve, then you're not that susceptible to changes in temperature in your system. And here is sort of the main difference between the orifice and the throttle valve. So here we have cut it along the axis of the valve, just to show how it's going to look like. So the main part of a throttle is that it has sharp corners, which means that it's going to create a lot of turbulence when the flow passes through it. The same goes for the orifice. It is also going to create a lot of turbulence, but it has a nicer flow along because it doesn't have these 90-degree corners all everywhere. So it has a nicer flow than what the throttle has. So it's a more easy flow on it. And we can regulate the volumetric flow rate. And usually this is done in combination with pressure relief valve, just to make sure that we get a certain amount of pressure drop once we get to the other side of the throttle valve, because we really do want there to be a pressure drop when we have gotten it across the valve, or else we can't guarantee that we have an actual volumetric flow rate reduction. So that we often have to combine these two in order to get it to work. And we can have a constant supply pressure because of this pressure relief valve, so that we get, instead of getting pressure peaks coming in at this size of the throttle valve, we're getting a constant pressure because all the pressure peaks are just being sent directly to tank by the pressure relief valve, so that we know exactly what we're going to get through the throttle valve, because we get, if it's supposed to be at 180 bars, it has 180 bars, no matter what happens before that with pressure peaks. It can peak up to 200 bars. It's not going to be a problem because the pressure relief valve is going to send it back to tank, so that we get the correct pressure drop across it. And the fluid flow itself that's going through the throttle point is dependent on the differential pressure. So this is why it is so important to keep the differential pressure at a certain level. So we want the supply pressure to be level, that it's not going to be peaking or anything, because if we're supposed to have 180 bars here and we suddenly get 200 bars, then we're going to affect the differential pressure, and that's going to affect how much flow is passing through the throttle valve. And we have this relationship that we can set up, where we have the differential pressure being approximately equivalent to the flow rate squared. So the flow rate that whatever is coming after the throttle valve, so the flow rate that is required of the hydraulic motor or the cylinder or whatever it is that we're using the throttle valve for. If we do that flow rate and we square it, then we are going to get approximately what we need in differential pressure. So the ratio basically between them. And of course, it will vary with the load changes, so that if if this is a cylinder and it's pushing something and it doesn't have any load when it's retracting, then we're going to have a varying differential pressure, because it has to deliver more pressure when it's pushing a certain amount of mass than when it's pulling back and it hasn't got any mass to affect it. So that also means that our flow rate will change in that case, because then we're not controlling the pressure on this side of the throttle valve. We are controlling it here with the pressure relief valve, but we're not controlling it after the throttle valve, so that then we will have changes in the flow rate. Which means that regular flow control valves like the throttle and the orifice valve, they are dependent on the load that's being applied to our system. And it also means that they are unsuited if we need a constant flow rate. If we do have to have a constant flow rate no matter what happens, if we have a hydraulic lift and someone is on that lift and they're jumping up and down so that they're creating quite a lot of load fluctuations, then we can't use one of these if we were supposed to have a constant flow rate in order to have a constant velocity on this elevator. So we'll look a bit at a system here. So I'll just get it up here. So we have the cylinder. It's supposed to move at a constant velocity to the side there, extend at a constant velocity. So we have a adjustable throttle valve, or an adjustable throttle valve over here, so that we can adjust the pressure, adjust the flow rate. We have pressure coming from a pump down here, and we of course have a directional valve to control it. So if we push the lever over on this side, we're going to open up pressure from P to A, so that we are extending the piston. If we pull the lever over on the other side, then we are going to open up pressure from P to B, so that we will be retracting the cylinder. And this one has a detent, so that it's going to stay in position once you've moved the lever, so it won't change its position by itself. So one thing that's been added to the system is the pressure relief valve. And that's in order to make sure that we have a constant pressure being delivered to the throttle valve. And then they've also put in a pressure gauge there, just to make sure that you can supervise your pressure and see that it's being kept constant. So this means that we have the correct pressure entering our directional control valve and then passing on to the cylinder. So then they put in a pressure gauge up here also, so that we can see the variable pressure there when the load changes, basically on the cylinder. And you're also getting the pressure drop across the throttle valve by comparing the P1 and P2. So the flow control valve means that we get a pressure increase up here, because it's basically blocking some of the flow, which means that it's creating resistance. And whenever we have resistance in a hydraulic system, it means that we have an increase in pressure. So that means that our P1 is supposed to peak once the flow starts going through the throttle valve. But our P1 is supposed to be constant, so that's why we have the pressure relief valve there. So that one opens up and lets the extra hydraulic fluid pass back to the tank, relieving the pressure a bit. Which means that we will have a flow rate that is divided between going up to a cylinder and going out and back to tank. So that we have here, we have the Q consumer and we have the Q for the pressure relief valve. So that we have one flow rate coming from the pump, which is constant, and then we have parts of it going up to the cylinder and the rest going to the back to the tank. And what the throttle valve does is to let through exactly the flow that we need in order to gain the correct velocity on our cylinder. And anything that is extra for the hydraulic fluid, that's just going to go straight through the pressure relief valve due to keeping the P1 pressure constant over there, so that it's sort of self-regulating that way. And if we look at this connection point in the middle, we can see that the pump that we have here, it is delivering 10 liters per minute. So that's the maximum, and it has a maximum pressure of 100 bars. But our cylinder is supposed to have, let's see, 96 bars in pressure, which means that this pressure relief valve has been set to 96 bars. So when we go over to look at our line here, that is the required flow line. Basically, if we had only wanted the cylinder to have 90 bars, we would have had 0 flow rate for it. It wouldn't be possible to move the cylinder in this case. If we had it at 92 bars, we would have had a very low flow rate for it. But right now we have 96, so we go over to the line of the needed flow rates. We go down here, we see that we are at, let's see, so we have 5 there, 7.5 there. Yeah, around 6-ish liters per minute on this one being delivered. And that's what we need to keep the velocity of the cylinder at a constant rate at this point, which means that the rest of the 10 liters per minute supplied by the pump, I'm doing it the wrong way around. We have the pressure relief valve on this side, so it's what's going to the pressure relief valve is 6, and then we have the rest is going to the consumer in order to supply the correct velocity. So that's basically the way we read off something like this. Usually, I can't really remember ever seeing one of these diagrams specifically whenever I've done any hydraulics work, but it depends a bit on what manufacturer you're working with. So this is how Festo, which have supplied the textbook, so this is how they figure out how much they're going to do, while Parker Hydraulics or Sun Hydraulics, they might have slightly different ways of figuring them out. So it depends a bit, but in this case, we get the remaining part here is for the consumer, and then we have what's going to the pressure relief valve on this side. So this is basically the extra fluid that we have is going to the tank on that one. So the volumetric flow that is not required, as we just said, it's going directly back to the tank at maximum pressure. So it's running back to the tank at full speed, which means that we have a considerable energy loss here because, as we saw from the graph, we had less than half of our flow was actually going into the cylinder and being used to move the cylinder. So more than half of our flow was going straight back to tank at maximum pressure, which means that the pump is working a lot harder than what it actually needs to do in this case. So if this is, if it's a system where you really need to regulate a lot of your flow, then it might be, and you only have one consumer that sort of regulates what the flow needs to be, then it might actually be better to have a variable pump, so that you won't have need for this throttle valve. You'll just have the pump regulating how much of a flow it's giving. That being said, a variable pump is quite a bit more expensive than a constant displacement pump, so it depends a bit on what you want to do. If it's cheaper, like here in Norway, to just have an electric motor going on water powered from the dams up in the mountains, then that would actually be cheaper than putting in a variable pump there. So you really need to look at the overall costs when you look at something like that. Yeah, the alternative was variable. So when we are adjusting, having adjustable flow control valves, we want to be able to create flow resistance, and we want to be able to regulate how much flow resistance we are creating. And we also want to be aware to say that the flow resistance that we've set, it's not going to be affected by temperature changes, so that it is independent of our viscosity in the fluid. And we also would like to be able to very precisely adjust the flow rate, and that is very dependent on the ratio between the cross-sectional area of the orifice where it's going through and the circumference of it, so that we can actually see how precisely we can adjust it by looking at the area compared to the circumference of the area. And with throttle and orifice valves, it is very inexpensive to make them, so they are very cheap to buy and use. So we're going to look at a couple of types, then we'll have a break afterwards, I think. So here we have a needle valve. We actually looked at that one also in the Christmas trees in the subsea technology. That's one of the designs that are used there. Where we have flow coming from beneath here, and it's passing across the needle and then out to the other side. So if you actually adjust the needle all the way down, it's going to act like a poppet valve, and it's just going to close off the opening completely. If it's possible to adjust it all the way down. Not all of them can be adjusted all the way down. But with these, you get an increased velocity, and you get high friction, and that's because you have this very long restricted passage past the needle, depending on how far down you've adjusted your needle. So you get much more friction in that kind. So it is dependent on the frictional component of the viscous friction of the fluid, because it has so much surface to pass across before it gets out. And adjustment possibilities is very unfavorable with regards to you don't really need to adjust much on the needle, so just turning it slightly on the threads is going to greatly impact the cross-sectional area, so that it's very difficult to do precise adjustments on it, because you so very quickly change the area in there. But they are very inexpensive, so it's because it's a simple design. You basically just need a pin and a threaded hole to put it in. Then you've got your valve. One other type that we have is the can't even read what it says there. I can't remember it either. It's the circumferential throttle. So this one looks a bit more like the one we saw in the clip, where you have this sort of crescent moon part, which is solid material, and by rotating it, so if we rotate it this way, we are going to start opening up the opening as we go along, and then we get more and more opening to have the flow through. If we open it all the way up, the crescent is basically going from this side and up to that side, so that all of the material is down here. and then we have full flow going through it. And it's the same resistance characteristics as a needle type. And it is also dependent on viscosity somewhat, but not as much as the needle type valve is. And it has the uniform cross-section enlargement, which means that just by adjusting it 90 degrees, you can get all of the adjustment in there. So it's a bit easier when you can, instead of having to rotate on threads and trying to see how many turns of the threads do you need in order to move the needle all the way down. In this case, you only need to rotate between 0 and 90 degrees to open it up. So then you can have a fairly large handle on it, and then it's very easy to get a very precise opening in amount of degrees in it. So it's also inexpensive and has a simple design, but it is a bit more complex than the needle type, so it's going to be a bit more expensive to use. Then we have the Longitudinal Throttle, which has the same resistance characteristics as the previously mentioned one, and it is a bit less dependent on viscosity than the needle type, but around the same as the circumferential. But this one has even greater precision adjustability. So basically, because we need to move the piston part further in order to create any reasonable change in the cross-sectional area. And it is also inexpensive and has a simple design. So then we have the gap throttle, which has an increased velocity but a low friction component. And basically because the flow only needs to pass this small point where it has much contact with the walls and creating extra friction. So it's very little dependent on the viscosity of the fluid. But for adjusting, it's not all that good. You need to rotate it 180 degrees, so a full half circle in order to get the full extent of the adjustment possibilities, and it's going to be difficult to see precisely how much effect you have on it. So it's not all that good for precision adjustments, but it is very cost effective. So it's not inexpensive. It's not a cheap valve to use, but compared to being very little dependent on the viscosity, you are getting quite a lot of effect for your money when you're using one of those. And then we have a gap throttle with a helix. So it's basically the same principle for these two. The difference is that for this one, you have originally a cylinder that has been just cut straight off, so that you've made an angled cut straight through the cylinder on it. So that when you rotate it, you will sooner or later get the long side of the cylinder to block off the opening there completely. But with the helix one, you have started off with a cylinder, but you cut it in a helix so that you have sort of it sort of follows the rotation of the cylinder as it goes along. So it has also increase in velocity and a very low friction component. So again, it's not really dependent on the viscosity, but it's very precise when you are adjusting it, and you can rotate it 360 degrees, and you get to be able to adjust it over the entire 360 degrees, so that you have quite a lot of room to adjust it in. But it is expensive because it's very expensive to machine this helix part on the cylinder. So then we'll do a break. give them a small minute to return. Okay, they'll probably be in any moment now. We'll start off by watching this clip, which is an adjustable orifice valve, or throttle valve, rather. It's called a diaphragm control valve.
Someone created a plague.
See how you get a really smooth opening, and you can have very good control of the opening and how much flow you let through there. So a valve like that would have been total overkill in a hydraulic system, because it's meant to regulate huge flows under high pressures, so more in a processing plant. But it still shows the principle very well of how you can regulate the cross-section of the opening in order to regulate the how much flow you get past it. So whether it is in that case where you're actually opening and closing a hole in the middle, or if it is that you are somehow restricting flow through the opening, so that you are closing it from a side or something, so that you are making it smaller. So the closest one we actually get to the diaphragm valve in the different throttle valves we looked at was the needle one, which will be the opposite one, where it is actually blocking off an area in the center and allowing flow on the sides instead, so that it will become the opposite of the diaphragm. So one-way flow control valve, it combines a flow control valve and a non-return valve, which means that in this case, when we have flow coming from the A side, it hits the poppet element and it just stops. It doesn't get any further there. So it travels up here to the throttle element, where it can pass through the throttle element and over on the B side at a lower pressure and at a lower volumetric flow rate also. Yeah, from A to B there. And the valve is pushed firmly into the seat. So again, you get Since it's a poppet, you get this leak-free sealing by it being pushed into the seat. And the flow can only pass through the throttle point. But then, if we have flow from the B side to the A side instead, we get the non-return valve opening so that it's lifted from the seat, so you can get full flow passing through it. But of course, you won't have complete full flow passing through here, because you do have a smaller cross-section there than what you have over here on this side. So some flow will actually go through the throttle valve also. But it still has two options of getting to the other side, and it's basically not being throttled at all. So you have a very minimal differential pressure loss across the valve when you're going this way. While when you're going the other way, then you have everything has to pass through the throttle valve. Yeah, so it has no effect. That could have been written as has no distinguishable effect. It does, of course, have some effect. It will always have some effect when you let the flow pass through something, a fluid flow go through something. It will always affect it somewhat. But if you put a pressure gauge on this side and a pressure gauge on that side, most likely you would get approximately the same reading on both of them. You wouldn't actually be able to read what the difference in pressure would be. There would be one, but it would be very small. Yeah? Explain the top one or both of them? Yeah, the top one. Because when the flow comes in here, you have the spring element, which is the black parts here. And you can basically see it just a little bit there. So the spring is pushing the poppet into the seat there, normally. So if you have no fluid in your system, the poppet will still be pushed into the seat by the spring, so it will stay there. But then if you also add flow from this side, you suddenly have a piston side here, and you have quite a lot of pressure on this side, so it's being pushed even more firmly into the seat. So it's definitely going to stay there. So the only way the fluid can move is up here, where it can pass through this throttle element, which looks quite a lot like, it's not quite a needle, so it's probably a longitudinal throttle, this one, since it has this gap that's been cut into it. So that allows flow to pass through the hole here, and you get quite a lot of pressure drop over to the B side, and lower flow rate. But then when you get the other way, the pressure from this side is enough to cancel the effect of the spring, so it starts compressing the spring and it opens up everything, so you get full flow through it instead. And this is the basic symbol that's used for it. So you're basically combining an adjustable throttle and a check valve that you put in there, or non-return valve. I actually think the book doesn't use check valve at all. It only talks about those as non-return valves. But you will quickly see, if you start looking at manufacturers of different manufacturers, that most call them check valves. So that's why I'm using both when I'm talking, so that I'm used to calling them check valves also. So I sometimes forget myself. And of course, like here, you can have an adjustable throttle point. So here it's possible to adjust the throttle up and down to get a different flow rate from it. So up until now, we've been looking at the throttle and orifice valve types, which are the simple ways of adjusting the flow. Now we're going to look at flow control, which sort of are even more precise in how it does things. Of course, there wasn't flow control here. It is flow regulating valves it was supposed to be. Flow control was the previous one with throttle and orifice. Yes, it actually says, it says flow control, but it has to be flow regulating, because if you start reading through the text, it's the regulating ones it's talking about. So for the flow control valve, which we have been looking at before the break, we could set up that we have had an approximate relationship between the differential pressure and the square of the flow rate. But if we need to keep our flow rate constant, but we do have a load that is changing, so that we are going to get a pressure that is going to be changing on the consumer side of the valve, then somehow we have to manage to make the pressure remain constant also there. So that even though the load is changing, we have to be able to bleed off higher pressures, so that if we get a higher load on our cylinder as it's extending, then we have to be able to relieve that higher pressure that's going to create. So the throttle point then gets combined with a flow restrictor. So in this case, we have a regulating throttle up here, and then we have an adjustable throttle over here. So we're basically combining two different types of throttles to create the effect that we want. So in a let's see. Yeah, that one wasn't supposed to join us there once, but in the normal situation where we have flow going from A through here and up to B, we have a pressure on the B side, which combined with the spring is equal to the pressure on the A side. So that we have a set pressure difference from A to B. So it's not going to be a huge problem. We have a constant pressure coming in here. We have a constant pressure going out. That means that this one, the regulating throttle, will stay in that position. So it will have a full opening out to the B side of the valve. And we are adjusting the volumetric flow rate with the adjustable throttle. So if we have a pressure drop occurring across the adjustable throttle here, so on this one, no, on the adjustable throttle, we get then the P1 pressure, which we have on this side, which is marked with the dark red, and it's going across the area of the piston here and creates the F1 force that works on the slide. And if that F1 force becomes greater than the F2 force that is working on this side of the piston, which is basically the pressure that's on the P2 side, so the sort of pink pressure here, working on this side of the piston, which probably has the same area as on the other side, then it's going to start sliding over to this side. So if we get a pressure rise up here, then we can, that's sort of, if we have a cylinder and we get extra pressure on the cylinder so that we have a pressure rise on the consumer side of the valve. Then we have a pressure rise on the P3 side. And we will also have the pressure P2 that is inside here that will also be rising. And it will open up the regulating throttle here so that we will get flow going through it. So that we can basically, by having increase of pressure on the P2 and P3 side, we can open up more to allow more flow through. Because we want to keep the overall pressure difference between P1 at the supply side with A and P3 where it's going out to B we want to keep that pressure difference more or less exact, so that we can keep the flow rate constant going through here. And these are shown with the regulating sign like this. If we have no load on the consumer, then the spring force that will be working on the piston here, so FF as they have put it in the book, it ensures that it keeps a full opening because it keeps F1 and F2 in equilibrium, so that the F1 force on this side of the piston is equal to the F2 force and the spring force on that side. So that's why it's going to push it back over here so that it becomes open again. And the FF will be a product of, no, that's supposed to be F2. No, FF, when you're designing this valve, FF will be a product of the difference in the pressure and the area of the piston. So if you want to calculate how strong this spring needs to be, if you're designing a valve like this, you need to know how much pressure difference are you going to have from the A side to the B side, and then you have to look at how much force is that going to be equivalent to when it's pushing on the piston. And then your spring has to be at least that strong. So it has to be able to deliver at least that amount of force, preferably a little bit more, so that you are going to push it open when it needs to be open. And the same principle here goes for changes in the supply pressure. So if P1 also, if we get changes in P1, if we don't have a pressure relieving valve before this throttle valve, then it's going to have the same effect here, where this slide will be moving back and forth as the pressures change, and it will be opening up or closing, or just keeping it slightly open up here, so that it's constantly being regulated and fixing the differential pressure and the volumetric flow rate, so that we get both of them constant. And the areas where we use flow regulating valves is when we need a constant adjustable feed and we have varying loads. So for an example, in the circular saw, the Mantis circular saw, which we looked at, that I designed there, it would be desirable to have one of these connected to the hydraulic motor, because you would want the hydraulic motor to be running at the same rotational speed at all times. But as you are cutting into the material, the amount of material that you are actually cutting for each rotation of one tooth in the saw blade is going to be changing, because you are cutting into something that is circular, and when you start cutting, you are basically just touching the edge of the material, and when you get into the middle, you are cutting through quite a lot of material for each pass, which means that you have a lot of resistance on the saw blade coming in, which means that you will get a much higher load when you're in halfway through the material than at the start and the end of cutting through the material. So then you would want one of these to deliver the appropriate pressure and the correct volumetric flow rate at all times for it. So it's also used a lot in lifting mechanisms where you require very accurate lowering speeds. So that whether it is a cylinder that has been extended and it's being let down, and you need to be able to regulate the speed where it's going down very slowly, or if you actually have a cylinder that's pushing something downwards, then you also need to be able to regulate that. Or if you have a hydraulic motor running a winch that is connected to a wire and it's lifting something in a crane, then you would also want to have a very accurate control of the speed that you're lifting with, lifting or lowering it. So it's very very useful in such situations. So for the flow regulating valves, it looks a bit different when we start putting in our symbols here. As you can see in the previous one, we are basically just looking at this. That's just this part, where that's all it is. But if we are looking at how they are often built, we have this housing for it. We have different valve cartridges that have been screwed into this housing, and we have the A port here. So the A port is coming from in the room here, and it's coming straight into the housing. The same with the B port, that's going straight out of the screen here. So that's why it's just shown as a circle. So a hole has been drilled straight in here. Then a hole has been drilled in this way, and it's been plugged so that we won't have leakage out on that side. And a hole has been drilled straight through everything here, and a valve has been put in here. The same here, we have drilled a hole straight through, we put a valve in. Here also, drilled a hole straight through, put a valve in. There we have a hole coming in with a plugged end. There we have a hole coming in with a plugged end, and also here we have a hole with a plugged end. This drilling part here, that is just to be able to connect the B to everything else. So all of these holes that have been drilled and plugged, they are just to create sort of pathways inside the material, so that all of this is just a block of steel or aluminium or whatever it's been made of, where they have just drilled a lot of pathways. So you can imagine that you really do need precision equipment to be able to create all of this, to know that when I'm going to drill in here, I'm going to drill 50 millimeters in, and then I'm going to stop and pull it out, and then I'm going to come in from this side, and I'm going to drill in 120 millimeters, and then we're going to have just reached the other hole there, so that we have a 90-degree angle in that passageway. So you really need very good machinery when you're doing this. But how this one works, it is basically the same as everything inside this rectangle. So we have this first part here is the pressure regulating valve. So it's regulating the pressure before it's going into the throttle valve. And you can see it has pilot pressure from after the throttle valve, and it also has pilot pressure coming from before the throttle valve going in. So it's the same part as here. It has pilot pressure from before and pilot pressure from the other side, so that it's being adjusted there. You have a check valve in here, so that is probably that one. You can see if it says, we have regulating throttle on number 1 there. Then we have the non-return valve on the number 2. And we have the adjustable throttle, which is this one over here. And there's just the screw itself to adjust it. So basically, when we are looking at this symbol here, we can often sort of assume that all of this might be inside that symbol, because this is a typical way of doing it when you want to really show all of the functions inside a valve. Then you make a sort of expanded rectangle, and you put all of the symbols in there to show everything that's happening inside this housing. But just putting this symbol in, and maybe having some identifier for it, for saying that it has a non-return valve also, or check valve, that would be enough, really, in the system. But if you want to make really sure that everything is going to be understood for the function, then you can put it in with all of the different valves that exist within it. So here we sort of get the same. We have a flow rate being delivered from the pump. We have excess flow going straight to tank through the pressure relief valve. Then we're coming into the flow regulating valve, and it is being regulated by pilot pressure before and after the throttle valve. So it's opening and closing, seeing how much flow it's going to let through. It's going through the flow regulating valve. Over on this side, it just hits the non-return valve and it doesn't get anywhere because it's blocked off. And then it goes out to the consumer, making sure that we have a constant velocity when we are extending it. But when we are pulling the cylinder back, our flow will go back here and it will hit the non-return valve, open it up, and then we just have full flow going straight back to tank. So that for return in this particular system, we don't need to have any control over the return. And for the return, it can just go with full volumetric flow. It's not going to be a problem. But when we are going to extend it, we really do need to apply the throttle and adjust it to be the correct one. So we had looked at those. Oops, a bit too quick. So here we'll see a system where we have a cylinder which is being extended and it is not affected by any external force. But then we have the same system over on the side here where we have a cylinder that it's still being extended, but now it actually has some resisting force. So it's pushing on a mass of something, most likely. So it has something that's working against it. But since we have the flow regulating valve in here, we are getting the exact same amount of volumetric flow rate. We are getting 3 liters per minute in both cases. But we have differing pressures. So without the external load, we have just 5 bars coming into the consumer. But with the external load, we are putting in 40 bars into the cylinders because we need those 35 extra bars in order to counteract that force that we are getting in. And this means that we have a much larger pressure drop when we don't have the external load. So there we have 139 bars, and here we only have 104 bars as the pressure drop between before the throttle valve and after the throttle valve. But we can see that before, from what's entering the flow regulator, so the one that's opening and closing the flow, from that one and to the next, we have the same differential pressure and we have the same starting pressure as we're going in. And we can see down here also, everything is the same. So it's only when we get up here that we get differences shown in our system. But still, even though we have different pressures here, we are still delivering the same volumetric flow rate to our cylinder, making sure that it's still moving at the same speed. So even though we are suddenly pushing on something heavy, it's moving at the same speed. So we're a bit quick today, but I think that will work out. Today we were going to know how piloted double non-return valves worked, where when we have flow on one side, we will open up flow on the other side in the opposite direction. We were to become familiar with different types of flow control valves. We were going to get to know what was the difference between throttle and orifice, which is basically just the geometry of the opening. And we looked at different kinds of throttling valves. And we looked at one-way flow control valves. And we looked at flow regulating valves now recently. So there we have it. Then we'll continue tomorrow morning with more hydraulics before I go off to Stord and do my own studies there. So see you all tomorrow.